Okay, let's start with the next session about scaling analysis. So this session has two parts. The first part is about strong scaling, weak scaling. So it's more theoretical. And the second part is a case study. So this case study is more practical and may be useful to better understand the strong scaling and weak scaling introduced in the first part. So scaling analysis. First, the scalability of an HPC system is very important. Here is an example. So HPC system is used to solve a very large calculation by using a large number or even a huge number of processors, hundreds of thousands of CPU cores. So the scalability of HPC cluster is the capability to deliver more computational power with more processors. So here is an application, CP2K application, and using the entire Noctua 1 cluster, which has just retired recently. But this is still a very good example to show you the scalability of the calculation. Here, the plot, maybe the fonts are too small, but what I can tell is up to 10,000 CPU cores. As you can see, the calculation can utilize more than 10,000 CPU cores to get a constant speed up for some atomistic simulation calculation. Therefore, the scalability of an HPC system is really important. And regarding the scalability, with increased power of computation, it was automatic. Yeah, if we look at this plot from 1970s to 2005 or 2004, everything increases almost linearly. Everything, I mean, number of transistors, single thread performance, frequency, and so on. The only thing that was a constant 1, so 10 to the power of 0, constant 1 was the number of the CPU cores. So in the past several decades, we get increased performance for free, let's say. But nowadays, because of fundamental physical laws, the number of the transistors can still increase, but the single thread performance is not really increasing a lot. Frequency also roughly the same as, let's say, 20 years ago. And a huge change, a significant change was here, the number of the CPU cores. Even nowadays, a laptop has, I don't know, maybe 4, 8, or even more CPU cores. For Noctua 2 Autos, the number of cores increased dramatically. So nowadays, if we want to continue this scalability, especially for your application, you really need to take into account parallelization, how to utilize more CPU cores, more compute nodes, etc. And the change is basically for more efficient, energy efficient utilization of HPC. Nowadays, energy efficiency or power saving is an important issue. And for parallel computing, there are multiple opportunities to take advantage of energy efficiency and parallelization. Believe it or not, in the previous session from Alex, he already mentioned data level parallelization, the so-called vectorization. And maybe you also asked the question about multi-threading. This is also a level of parallelization. and multiple chips and multiple compute nodes, as you can see in those blades. And last but not least, to use the entire HPC cluster to run your calculation. Yeah, those are the opportunities for us to run computation with more parallel, with more energy efficiency. There are multiple ways to run your calculation in parallel. Here is a list of opportunities. So you can use ready-to-use environmental variables or tools. For example, MATLAB. I'm not sure if you are using it. And also use automatic compilers. For example, GNU compilers, Intel compilers, to take advantage of parallelization, or using libraries, parallelization libraries from vendors, for example, from AMD, from Intel, or to use language extensions. Maybe you heard of OpenMP or MPI, or just use programming languages that support parallelization directly. For example, Julia, Chapel, or Go. But today we are not going to dive into programming, to program parallel applications. We will do measurement. This is more relevant for HPC users. So your purpose is to make your calculation run faster. So that is why here we will focus more on the performance measurement. Before we do the measurement, I would like to talk about strong scaling and weak scaling very briefly. So this part, it is somehow theoretical. So how to measure the so-called speed up of your parallel application? So to do that, we can do some mathematical work. Assume we have n CPU cores, and the serial runtime is T serial, and the optimal or perfect parallel runtime is T serial divided by n, right? This is easy to understand. And then the speed up is serial runtime divided by the parallel runtime. And one important fact is parallel efficiency. So this is the ratio of the actual speed up with respect to the ideal speed up. So normally this is less than 1 because of some overheads, right? And then Amdahl's law, it was stated by Amdahl that only a fraction of your application can be parallelized. There are some fraction of your code that can anyway not be able to be parallelized. And then the speed up will finally dominated by the serial part, the remaining part. So based on those statements, there is a model. I'm not going to dive into this model into many details, but after some mathematical work, you will have the speed up, which is relevant to 1 over 1 minus p. P is the, let's say, the parallel part. So 1 minus p is the serial part. So as you can see, in the end of the day, the speed up is relevant with respect to the serial part. And if you plot this Amdahl's law, you will see something very interesting for the speed up with respect to the number of the processors, right? You may have this idea, okay? I run my application with more and more CPU cores. I mean, 100 CPU cores, 10,000 CPU cores, even 100,000 CPU cores. you will have, let's say, always increase the speed up for your application, right? But in reality, this is not the case. So here is the plot of the so-called Lambda's law, Amdahl's law. If the parallel portion is only 50% of your entire application, and then you will see this blue line that the speed up will be 2 with, let's say, whatever number of the CPU cores you see here, 1,000 CPU cores, 2,000 CPU cores, even 65,000 CPU cores, right? Because the serial part will become the bottleneck very quickly. If the application has 95%, this green line, that can be parallelized, and then according to Amdahl's law, you will have maximum speed up of 20. So this looks, not ideal because we are expecting 1,000 times faster, but according to Lambda's law, this parallelization, this does not really work because in the end, you can achieve maximum 20 times faster with, I don't know, 1,000 CPU cores or even more CPU cores. So basically, Amdahl's law suggests that parallel computing does not really work. But in reality, parallel computing is very successful in practice. And the problem is because Amdahl's law assumes the problem size is a constant. Yeah, this is the so-called strong scaling. But in reality, we can increase our problem size, for example, by simulating a large problem. To be more specific, let's say we increase our simulation, let's say, number of atoms from 100 to 200 to 300 and so on. We can increase the problem size instead of using a constant problem size. And then Gustafsson argues that we may measure the so-called speed up by scaling the problem size instead of runtime, so that we can utilize a large HPC system to solve a much larger problem, to simulate large, for example, large collection of atoms. And then for Gustafsson's law, a key is here. The speed up is now measured by means of the workload, right? And within a fixed runtime, we can increase the workload. And the workload is, let's say, proportional to the number of the processors or the number of the CPUs. And for the serial workload, we use WS. For parallelizable workload, we use WP. And then we can do some mathematical work. And with one CPU core, W1, we have this kind of work. With number of n CPU cores, we have more work that can be done within a given amount of computation time. And then with increased number of n, we will see that in this case, we are able to do more parallel work. And this is, let's say, linear. This increases linearly with respect to the number of n, so the number of processors. And in this way, we are able to utilize the HPC resources to run more calculations. So for scaling analysis, there are two types. One is strong scaling proposed by Amdahl. So basically to measure the runtime for one input with a fixed problem size. Another one is the so-called weak scaling. So the computation time is fixed, but we can increase the problem size so that we can utilize large HPC clusters, as you can see here, to solve much larger problem. Yes, I fully understand this part is more, let's say, theoretical or mathematical. That is why we are going to give you a case study for the so-called N-body simulation. So N-body simulation is very, let's say, simple but very useful. N-body means we have N particles. They have pairwise interaction like this one. You know, two particles, they interact with each other. And this is, and then we calculate the positions and velocities of those particles, and then move those particles with respect to their movement. And this N-body simulation is very useful in many fields, for example, in astrophysics or in molecular dynamics. So for this small case study, we just determine the position and velocities by using Newton's law of motion, and then to calculate the force using the universal gravity, gravitation, and then to move those particles from time 0 to time 1, time 2, time 3, you know, with these time intervals, and then to run the simulation. This N-body simulation has a lot of parallelization inside. This means, for example, here we have a box of many particles, let's say 100 or 1000 particles, and then we can divide this box into process 0 on compute node 0, process 1 on compute node 0, and so on. And then to let each process to calculate the forces, the interactions only for those part of those particles, and then to do those work in parallel, and then to summarize the result, and then to move the particles to the next positions. And besides parallelization, here, those calculations also need communications so that the positions of the particles, for example, can be communicated between different processes. This will introduce communication and reduce the scalability of your calculation, because communication does not calculate anything, right? And in order to do this, we write a Slurm job script with increase the number of compute node, as you can see here. And then for each compute node, we use different number of tasks or different number of MPI processes from 1 to 128, and then extend the calculation to multiple compute nodes from 1 node to 2 nodes, 4 nodes, 8 nodes, etc. For the purpose of demonstration here, we are using up to 1000 CPU cores, to be more precise, 1024 CPU cores. So basically, this is about 8 compute nodes here on Noctua 2. So the ideal situation is with more and more CPU cores, as you can see here, 1 CPU core to 1000 CPU cores, we are expecting this blue line, right? With continuously decreased computation time or wall time. But in reality, our measurement gives us something like this, right? With 1000 CPU cores, the calculation becomes even slower than, I don't know, maybe 8 CPU cores. So this makes no sense, right? 8 CPU cores is doable everywhere, even on your laptop. But with 1000 CPU cores, as you know, this is quite a lot computational resources, but it becomes even slower. And the scaling for one single node is okay, but still, not good. If you look at the speed up with respect to the increased number of the CPU cores, the speed up is, let's say, horrible. So what to do if your application does not scale? Yeah, this is, I think, the most important question you would like to ask. So a simple solution or a solution for a poor man is to use less CPU nodes or even use less CPU cores. Because if more CPU cores do not help, why not use less CPU cores? For example, use one compute node or even only one CPU socket. And or you can run multiple simulations on the HPC clusters. Instead of launching one job using 1000 CPU cores, you can start, I don't know, 100 jobs, and each job use, let's say, several tens of CPU cores. And last but not least, you can report this scalability problem to the developers or to contact us, PC2 support, and we are happy to look at the performance problem with your application together. Let's say, after some consultation or studying together, we really improved the scalability of the code. Now you will see that the improved measurement, this green line, is almost identical to the blue line. Yeah, up to 1000 CPU cores. Here you still see some differences because the runtime is really too short. If you look at the time scale, this is less than 0.01 second. So for this small time, you see the discrepancy from the ideal scaling. If we look at the speed up, you will see that this time we have almost a linear speed up for our calculations up to 1000 CPU cores. So after giving you this case study, there are some hints for scaling analysis. So before you start, let's say, a production large-scale calculation, you may want to choose a relevant example, and if necessary, make some simplifications, but sometimes not to make this example too simple. And also, you may, if your calculation is iterative, for example, to calculate some value depends on the previous value, you may need to find out if everything or if the same thing is done in every iteration, or maybe try to do some timing for individual iterations, because the floating point calculation is not really, let's say, exact for computer. Or try to make your calculation as reproducible as possible, for example, by using a fixed random seed. And also to repeat benchmarks if necessary. And if you see some fluctuation, this is a signal of performance issues. And yeah, you may want to dive into it, or you may send us mail so that we can look at the performance issue together. So before we continue to the next part, I would like to give you some more detailed demo for the hands-on C. So basically, hands-on C is to use CP2K calculation, this CP2K calculation, as an example to show you why scaling analysis is important and how could this help you to optimize your own calculation, right? So the first exercise is very simple. There is an example job script. Yeah, by reading this job script, you need to identify the number of the compute nodes, number of MPI process, OpenMP, or CPU cores, and so on. So this is, can you see my terminal? I think this is easily visible. Okay, great. So if you look at this example job script, you will see, okay, I'm using one compute node and two tasks. So basically, two tasks means two MPI processes. And each task is using 8 CPU cores. So why here 8 cores, not 7 cores or 9 cores? Because you have learned the CPU architecture from the course, from the section from Alex. Yeah, Alex said there are 8 CPU cores grouped together. So that is why it would be more efficient to use a group of 8 CPU cores instead of 7 CPU cores or 11 CPU cores and so on. And then you can count the number of the resources used here and then run the simulation. And let's go to exercise 1. And to get the runtime, runtime is the key. You can use grep command. So for this calculation, it took 14 or maybe 14.8 seconds, or roughly 15 seconds. And in order to do more parallelization, you may want to use more MPI processes, more compute nodes, and so on. So you can run your calculation. Here, I have exercise result 2. So here you can take a look at the code. I'm using three compute nodes, 64 MPI processes, lots of resources to run the calculation. And if we take a look at the time, this took 5 seconds. Okay. It looks not really optimal because 14 reduced to 5 with lots of resources. This seems not worth it. And then the last exercise is to do some tuning for one single node. And for this one, you can change the number of for example, the CPU cores or MPI process and so on. Here, as you can see, I'm using one compute node with 24 processes, and each process use 8 CPU cores. So if you do the math, 24 multiplied by 8 is 192. It's exactly the number of the CPU cores for one compute node. And then if you grep, okay, this takes 4 seconds, even better than this one with 3 compute nodes. Now you see, you really take advantage of using the resources more efficiently, also with more benefit for the speed up. Here, one compute node, 24 processes 4 seconds. But here, maybe you still remember 64, lots of resources, 3 compute nodes, and so on, but even slower. So I think this is the message that I would like to emphasize. Yeah, think about to optimize your calculation job seriously, because you can really benefit from it. I think that's all.